All right. So I'm not sure. Unfortunately, I could not see other talks in the school. It's a very well-known school, and I'm really proud to be able to show some of the work here. Among all those research interests, I picked one which is relatively on the side, but which I exploited a bit in the last few years myself. And in fact, now there's a PhD student with Politecnico di Milano, Matteo Matteucci there, being supervised, not following exactly these lines, but working on benchmarking of robot systems. And I mean, among the topics, Michael apparently suggested that it could be this one. So it's not, I used to make presentations which usually have a good component of practical robotics, videos and so on. It's not going to be the case. This one is really more to stimulate or not you intellectually, hopefully to stimulate you positively intellectually, not too boring. For something that people usually don't pay so much attention in robotics, and that some of us have been doing some research on lately, which is how to benchmark robot systems. And in my case, I'm going to describe a probabilistic approach, and you will see how this came up from all the notes. So a brief introduction to motivate you is that, I mean, there's a lot of papers in robotics that suffer from what we call the Look-Mano hands syndrome, right? I mean, hey, here's a great robot, it works fine. And in fact, to be honest, I think it's really great, even better than showing no real robotics at all, which is what I'm going to do here. But it is good to show great robots that do very interesting things, but it would be even better if we would have means of benchmarking them, comparing some solutions for problems in robotics to others that other people develops. And so what's the alternative is what we call benchmarking. And this all comes from people that have been pursuing this quest and trying to bring into robotics the so-called scientific experimental method, where, I mean, not everyone completely agrees on this ontology, but somehow one way or another it gets close to the idea that the experiments we make in this particular case in robotics should be replicable. That means that they should be reproducible. That is, it should be possible to verify in an independent way that the results of a given experiment, so that I can then reproduce it. And of course, that requires that we fully document everything, parameters of the experiment. Not always this shows up in the papers, though it should be good practice in general, not only for robotics. And repeatability. The fact that that's really very much connected to the Look-Mano hand syndrome. I mean, it should not be enough to show the robot working once well. It should work several times and be resilient and robust to different conditions and so on. So it should have the results should have statistical significance. We have been, some of this actually showed up for other reasons, but some of us, and I'm talking particularly of myself and Matteo Matteucci in Milano, for instance, have been kind of pursuing this path under the frame of robotics competitions. We started, I was the coordinator of one of the two first projects funded by the European Commission on competitions in Europe, and it was actually the idea was benchmarking through competitions. And in the Rockin project, we developed things like common test beds, code sharing, using referee boxes. Some of these things were coming. For instance, the referee box is inspired by other big endeavor that I've been connected to for years, which is RoboCup. These are things that allow people to reproduce results. I mean, we have a network of test beds now for domestic robots in Europe, where the teams can go and get results, and they are considered to be comparable to the other test beds because the test beds obey a minimum set of rules. And repeatability is that we are doing, and this is was very peculiar of Rockin and not so much, for instance, in RoboCup, is that we do several runs and we do them instead of in so much kind of motivating people to bring an amazing novelty, is more to make their robots robust and resilient, and so that we award doing the same good thing several times and not just once. Even though we may sometimes change a little bit the settings between the experiments but do it systematically through the referee boxes, which communicate to the team without the team knowing a priori, communicates to the robots what they should do. So let me do a few definitions, because one of the problems in this area is that there are no standard definitions, and we had a huge discussion in Rocking about this, and we ended up with some definitions, which are the ones I'm showing here, or a subset of them, which at least pave the way for you to know what I'm talking about. You may not fully agree, but at least you know when he talks about metric, benchmark, score, whatever, he's talking about this. So metric is seen as a quantitative and precisely defined criterion to assess one or more aspects of the performance, or either of the robot system in full, or of a functional module that is part of it, like localization or a local planner or whatever. Benchmark is then the process of evaluating the performance of a robot according to a specific metric or of one of its functional modules. We also have the score, which is the result of applying a task benchmark or a functionality benchmark to the performance of a robot system subjected to an experiment. This definition is important because if we do benchmarking through competitions, we define the benchmark, and then from every time the robot does the several runs, we get a score, and we use the score to classify it and to rank all the robots in the competition. I won't talk much about competitions or anything else today, except for a reference here and there. But since it has motivated a lot of it, it's also important to mention that this other thing in this slide also came from the Rocking project, and I'm going to use it a lot. It's another thing which is subject to a lot of discussion, and the names we use are just these, and so bear with me when you see me using them. So if we have, you see my cursor, I hope. If not, let me know. When we execute a task, it is usually composed of several modules, which in this case we call them functionalities. People can call them subtasks, primitive actions, whatever, abilities. We call them functionalities. And what happens is that we can, as I said before, either benchmark the full task, and for that I'm not going into details, but we introduced a schema that is being used still today in the European Robotics League, which is basically based on achievements and penalties. So if you have a set of achievements, like you got to the room, you were able to make yourself understandable to the person, you get a point for each of them, and you get some penalizations for things like bumping into obstacles or getting too close to the person or whatever. And then you are classified in classes according to the number of penalties, and inside each class according to the number of you are classified in classes according to the achievements, and inside each class according to the penalties. But we also do the benchmarking of the functionalities. And the functionalities, in fact, can be used by different tasks. And in fact, they may perform differently depending on the task where they are, but we benchmark them isolatedly with specific conditions which are the same for all the teams and for a given functionality. And we also have a lot of that with using even motion capture systems, like, for instance, for the functionality of localization or object perception, but we always have the same waypoints for all the robots, or the same localization of the robot that is trying to identify an object, while in the tasks, as we will see, and this has an impact on what I'm going to talk about, they may arrive at different locations, they may have different relative positions to the object, for instance, when they get there to recognize. And this has an impact on the task value if we propagate it from functionalities to tasks, which we will do sometimes. So very often, what we do in benchmarking through competitions is to use score to rank the teams, and the benchmarking to study the impact of the functionality benchmarking on the task benchmarking. And also to provide, which is more obvious from the definition, reference performance against which the researchers can compare the performance of their approaches. Okay, so let me now dive into what I call my probabilistic approach, independent from systems, to benchmarking. And this is the core of my presentation. When we look at robotic systems, I think one of the reasons why people usually refrain from trying to apply the experimental method is that they are composed, the scientific experimental method, is that they are composed of several subsystems. I mean, I'm naming a few here. like controlling the joints, localizing the robot, doing guidance, doing path planning, doing task planning, which are of completely different nature and measured in many different ways using different units. There's even some benchmarking in the literature for each of these, but then people do not care about benchmarking the execution of the fully integrated system in a complete task. So the question is how to evaluate with benchmarking purposes the performance of distinct subsystems, which I think is like looking at the problem like the Babel Tower. And the proposal is to use the common language of uncertainty quantification to evaluate performance, and that language is probability theory. How do we do that? So in fact, when we were discussing this at some point, even though we followed a completely different path in rocking, I was discussing it with Matteo and other people. Fabio Bonsignori, who was very active in this area as well, actually is the one that is pushing it more in the European and the worldwide community of robotics. It came to my mind some old work I had done, actually in my PhD thesis with George Saridis back in the 1994. And the paper I cite here is from 96, right? It's a book, there's also a paper, which was not done for benchmarking, but which in fact could be used for it. The idea was to do a joint consistent definition of reliability and cost. And that one could apply to any subsystem and then could be combined into the performance of a whole task, which composes all the subsystems. And, well, I kept talking about it. It started, I don't know, maybe around 2013, 14. And finally, after being a lot pushed to do it, I succeeded to have a paper accepted about it in IRUS 2018, which is the kind of the revisited work in a much more modern perspective and really thinking of it as for benchmarking. In this approach, I abstract problems and algorithms. So, which is a notion used widely in computer science, but for instance, a functionality is a problem, imagine localization, but the functional modules are the algorithms. Say Monte Carlo localization is one algorithm, extended Kalman filter based localization is another algorithm to solve the problem of localization, excuse me. The same way, a task is a problem, and the different plans to solve it will be seen as algorithms. When we talk about tasks, now there are the two levels all the time. And so, yeah, in the end, what we want, I've said it already, is a joint definition which enables using reliability and cost so that we can also use it not only for functionalities, but propagate it for tasks. Well, why functionality and cost? I mean, it should be somehow obvious, but I'll better talk about it before I get into the formula that I use. Because, of course, the idea is what we are assuming here is that every task, every system, what you want it to be is reliable. That is, to perform above a given level of certainty when you apply it several times. Since the uncertainty is a feature, not a bug, and so you have to live with it. But of course, what you could say is I want to increase the reliability until it gets to 99.99999%. This usually has a cost. So what we have to do is to balance it. But we have to define it in a consistent way, the two entities. And that's what this simple formula did. That one I introduced in my thesis. So that's the old thing. But I'm going to explain it term by term to make it easier for you and just avoid all the math jargon and so on. So first we define reliability of an algorithm and also of a problem element, which I will tell you what it is in a minute, as the probability of the approximation error when I solve the problem by that algorithm is less than a given desired accuracy, epsilon. I'll give you examples, so don't worry if you don't fully understand it now from the abstract definition. That can be, this was described in words, that can be kind of mathematized by saying that this is the probability of the norm of the problem desired solution minus the solution approximation obtained by the algorithm. So the desired solution only depends on the problem element, that is from the image I'm using, from the system model I'm using, Here, of course, the solution depends on the algorithm. So the norm being less than epsilon. The cost, which I'm not yet defining consistently with reliability, usually this is just a brief reference for you to know, usually has two components. Is the cost of getting the information for that problem element, so this calligraphic I is the information, and the cost of processing it. So usually we think only of the cost of processing, but of course we should also think of the cost of getting the information. Imagine you want to do the average over several images to then process it using edge detection or even doing deep learning over the image to recognize objects. You might want to do first some kind of learning, and to get that information also as a cost when you are training the network, or when you are doing the several images average. And that's very important too. So the joint definition is now here. The point is the following, and bear with me here. We want from all the possible reliabilities of algorithm phi for the problem element E, we will look at the problem element that leads to the worst case scenario, that is the infimum of all the reliabilities. But I mean, from a set which is all those which are greater than or equal than the desired reliability, that level above which we want to be. So we want the system to perform as good as 90% of the time. So we pick the one that gives you that infimum, the arg of the inf. That's the optimal problem element. We replace it in the cost and in the reliability, and we have the cost and the reliability of the algorithm. So they are defined consistently. That is, for that problem element that led to the set of possible reliabilities which satisfy our specification, we get the worst case scenario, and that's the one for which we compute the cost and the reliability. And the cost function then is as simple as, if we have the cost normalized between 0 and 1, the reliability is always between 0 and 1 because it's a probability of a discrete set. This is just cost minus reliability. So we want to maximize to minimize J, that is minimizing the cost and maximizing the reliability and getting the balance, equilibrium between the two. So we want, in the end, the algorithm phi that minimizes J for a given desired reliability RD. Here are examples that hopefully will clarify what I've been talking about. The functionalities that I'm talking about here are three completely different ones, so that I can illustrate how this can apply to any level of abstraction in different subsystems. One is move joint, of a manipulator. Another one is follow path by a mobile robot. Another one is locate object by a vision algorithm. And here I have the problem element, the desired solution, and the output of the algorithm. Say the problem element here is the closed loop controller I'm using for the move joint. Could be different ones, of course. S of E is the set point that I want to achieve for the joint, like a given angle. And U of phi is the output of the control algorithm, like a PID or a nonlinear controller or an MPC that I use for that problem element, for that particular closed loop controller, the parameters that I use for it. So imagine these are different this is a PID, and these are different parameters of the PID. For the same problem element, I have different algorithms, and this is the output of each of them. That's the U. And of course, it will get to S of E with more or less error. And I could have other specifications like overshoot or rise time, traditional things in control. In a follow path, we go like a higher level of control. We have the guidance, navigation, and control loop. That's the problem element, for which I can also have different types of algorithms. And I have as a reference the desired path, while here, this is the output. This is the path that I really follow with a given algorithm. For locate object, this is the problem element of the images. S of E is the object location, the real object location. And the algorithm, the U is the algorithm for object recognition from the image. Gosh, this keeps jumping. Just to give you a hint, because I'm going to focus a lot on reliability of what the cost could be the sampling rate of the control loop, the number of particles in the self-localization algorithm, the number of images required to be averaged. So one example for each of the functionalities. I mean, I don't know if people can interrupt me if there's such functionality. I don't see anything, chat and anything else. So, but if you can and if you have to speak up, please do, if you have questions. Let me detail a little bit more these examples. For instance, the move joint. Here it is. I mean, this is the desired final joint value. This is what different algorithms get, and I kind of sketched them. This one would get a zero error, while the others would get some error. And they could even be applied several times. There might be uncertainties due to noise in the sensors, due to poor modeling, and this would tell us the reliability of achieving this error. And this would, and of course, it would come with a cost, which is the number of computations I have to do plus the sampling time I need to compute the algorithm. For follow path, the guidance system would use as reference the sides of the lane, which, for instance, a vision algorithm will identify, and well, different algorithms will come up with different use for this same part of the road. Other part of the road would be another problem element. Problem element can be defined in a very broad way here, as you maybe already understood. But say one of them could take the car inside the road very nicely. Another one could take you outside of the roads. I mean, if people are drunk and you don't want that, but anyway, they are comparable. I think I had, yeah, this one, another one, yeah. So then there may be different results. In locate object, this is an image processing. You can use an image processing API. And for instance, this is an image taken from a paper of 2011. You have the object that you are trying to recognize from the image, but not only that, you want to determine its pose. We have actually this functionality benchmarking in ROCKIN and in the European Robotics League. So we put the object in a given place. We have a motion capture system determining where the object is. And we know, of course, what the object is, but the system has to recognize the object and to determine its pose with high accuracy. And everything counts. In this case, the pose requires knowing the location and the orientation. So we have a frame associated to the object, which is in this case S, should be S of V. F is an old notation for the problem element. Sorry for the mistake. And you say that our algorithm determines something like this, this or that. So with errors in location and orientation. Well, in this case, I might not tell you anything, but I want to give you some food for thought. This is a case of a primitive where we actually, while before we know what are, we can determine what is the reference signal from, it's either given or processed by a vision system that gives it to us. Here we don't know. Unless we use the motion capture system or some predefined information, we don't know it. So when the primitives are like sensing primitives, we have a problem because we don't know S of V. And we have to find how to overcome that. One possibility is to use precision, not accuracy, like the average of the different clusters when we observe the object several times and determine its location. It might have a bias with respect to the ground truth. Or we might say that we don't allow this kind of sensing primitives. They really have to all be kind of sensing act loops, closed loop things, because then we always have kind of a reference. So this would be, imagine a visual serving problem where this would be part of it. I need to recognize the object and then get there and grab it. There I know, I mean, my reference is to have zero error and grab the object. And the localization of the object is only part of the problem. Like using localization in the GNC loop, in the guidance, navigation, and control loop, instead of localization being functionality. Okay, now, the main, so this is the core part of my talk, and now is the core part. When I talk about a task, I said it was composed of functionalities. And I said we could apply the method to functionalities or to tasks. The thing is, should we apply the same definition separately to functionalities and tasks, and that's it? or should we attempt to propagate the functionality's performance evaluation to the task performance? I mean, it could even be interesting to see, okay, what is the impact that this functionality has on the performance of the tasks? So, and then compare with what really happens when I compute simply the performance of the task without considering this propagation, to see if it makes sense. And there was some work done in that direction, but I'm not talking about it here. The thing, if we attempt to propagate, how do we propagate? That's the point. We can look at things that exist in the literature, which, even though they are not directly talking about that, somehow do it. I mean, the well-known decision theoretic planning approach, under uncertainty approach to task planning, what it does is to consider a performance function, which is the summation of the future rewards with possibly a discount over a given time horizon. And so every plan is a sequence of actions. So every phi is a different sequence of actions starting from state x. RT is the reward received at time t. And from this, we determine the value of each state, and indirectly, we determine the policy, that is the map from states to optimal actions. And when we do that, we are actually taking the actions that maximize the performance function. If we use the approach A, that is doing independent things, I mean, we can just go and check the reliability and cost of the different algorithms, the different plans in this case, that lead to a particular action sequence. Different plans could differ just because they use different gammas, for instance, discount factor. And of course, molding also the different rewards based on the goals that we want, whether it is just to get to a desired cell, or pathing through a given sequence of cells, or avoiding a bad sequence of cells, or so on. So in that case, we would just compute directly the performance of the task, and we could also do that for the different the different actions that we use, like the action of moving from one cell to another, but it would be completely independent. So in that case, the task would be the problem element, phi would be the plan, S of E would be the set of goal states, and U of E would be the actual sequence of states, which might not be as good as the one we desire. If we use approach B, however, we should first determine the J for each functionality, say the motion functionalities, and we call them FF, and then propagate the performance evaluation using the accumulated discounted reward formula. That's what would be done under this setting. As we will see, this is not appropriate for our setting if we don't take care. But that will come later. So this would be the performance of the task, FT, starting from state X. In that case, is the performance of the algorithm that represents the plan. And it would be the accumulated discounted summation of the performance of each of the functionalities at different time instants, by the way. Let's see if we follow approach B, what happens, and then we will see. So we abandon approach A now, but then we will see how, in a case like this, it could also be used in something as well known as sequential decision making under uncertainty. First of all, let me just tell you to wrap up this part, that for both approaches, we can solve the problem element, which is the task. I mean, the problem is the task. The problem element is FT. Can be solved by different algorithms, which are the plans, and we call them phi. The metric is J of FT, and it's in this case interpreted as the accumulated discounted J's of FFs, where the FFs are the functionalities. And the best plan, of course, is the one that maximizes J of FT. We actually, I like a lot representing plans by Petri nets due to a lot of reasons. And this is an example where this is actually done similarly to what we were talking about before. But Petri nets by themselves can model a system and analyze its performance in a kind of a similar way. For instance, imagine this barman robot whose actions are depicted here in a very simple manner. I separate the controller from the environment, controller in red, environment in black, and the robot can be either idle or helping the client or picking the beer. I'm not going to explain you how Petri nets works. If you know, you will understand this easily. Otherwise, sorry. But for instance, if the robot is idle and the client is waiting, so the conditions are satisfied to jump to bot helping client, but the robot can also be idle, and if the beer glass is ready, it can go there and pick it. And probably a supervisor should tell it to first go and pick it and then serve the client. But this would be at a higher level of decision, which could be motivated by the expected performance, which could be based on a stochastic modeling, using now another view of the Petri net, which is a stochastic Petri net. In this case, what we had here are things like the client dispatching rate, the client arrival date, the picking beer rate, the glass filling rate, all things which depend on our robot system, so how fast it is able to pick the beer glass, how fast it can fill the glass, and others depend on the actual environment, like whether the clients arrive, there's a lot of them arriving or not, if they are very interested in being served by a robot or not. And what happens is that we can compute a Markov chain from this model and compute the performance of the different states of the controller and actually of the full robot system, controller in closed loop with environment, and so we can end up with a performance value. So again, the same idea. So what we could do is to use for these what differs is what we use for computing the performance. And here we are proposing to use reliability and cost. It so happens that in the Petri net, the thing ends up being equivalent to a Markov decision process, and so the solution is very similar to what we saw 3 or 4 slides ago, and provides the performance of any plan starting from a given state X and the optimal selection of functionalities per state, such as the one I told you, whether you should go and serve a client or go and pick up a beer. Now, let me dive, and this will be my final part, into how we propose to do this approach via propagating functionalities to functionality performance to task performance. And I will focus on the reliability because then the cost is more simple, and I'll also show it on only one slide. So the important point is again to repeat that the definition is consistent between cost and reliability, so we can use them together. And it applies to different levels of abstraction. So we can do it for the functionalities, and then we can either compute it also separately for the task, that would have been approach A, or compose the functionalities performance to obtain the task performance. Because tasks are compositions of functionalities, somehow executed in parallel, in a sequence, whatever. So how do we do that? The problem elements of the functionalities are used by the functional modules. This can be the images, the controllers, and so on. In the tasks, I had not mentioned it yet. These are the events, the world models, the shared data, okay? And they are used by the different algorithms, which we said before are the plans. Now, for a given task T, we know that the performance J of task T for the algorithm for the plan phi P is given by the cost minus the reliability for the task. And the best plan is the one that maximizes this, that minimizes this. So let's look at an example. We have this algorithm, and I mean, this is a free representation of sequential things and parallel things. So this means that they are starting being executed in parallel from here on. So after I apply the functionality 1, I apply in parallel 2, 3, and 4 with the current algorithms. And then in the end, they finish, they kind of synchronize, and they go to this sequence of F5 and F6 in parallel with F7. They also synchronize in the end and end up with F8. If I would assume that all the functionalities are independent, this would mean that the reliability of the task would be as simple as the product, since these are probabilities, and I'm talking about a joint probability of all the performance of all the functionalities, which, because they are independent, ends up being the product of those probabilities. The probabilities are at the root of the definition of the reliability, so this would be a product of reliabilities for the n functionalities, 8 in this case, okay? Unfortunately, life is not that simple. I mean, in fact, they are not even usually independent. A very typical example, which I mentioned before, is if you have a mobile manipulator and the robot with the manipulator approaches an object it wants to pick or a handle it wants to use to open a door. The performance of this functionality pick object will depend on the actual performance of both the move to object that took the robot closer but not always to the same pose with respect to the handle, and also, of course, of the image processing algorithm that locates the object. So these are functionalities carried out before pick object, and though I might characterize the performance of the pick object by controlling the conditions and doing that several times, we do that in functionality benchmarking in the European Robotics League, when it is used in different tasks or by different algorithms in the task for the other functionalities, it will end up performing differently. Sorry. So how do I handle it? Well, since we were looking at the joint probability of all the functionalities, let's use the Bayesian formulation to decompose this into conditional probabilities. So we could use Bayes formula recursively, and we could assign some arbitrary order to the functionalities without any loss of generality. And so we would have the reliability of the task as being the reliability of the functionality n multiplied by the reliability of fn minus 1 given n. So this could be like the sequence of tasks in a sequential application, and so on and so forth until I get to f1 given that I have applied all the others. Okay, so this is the probability, and each of them is the probability of this being less than epsilon, as we have defined before, now conditioned by the execution of all the others. This is just repeating the definition and making sure you understand that now it is a conditional probability. But the problem again is how to estimate the conditional probabilities. We could say, well, it only depends on the previous one. Well, it would be a bit simpler, but still, how would we estimate the conditional probabilities would be a problem. However, there's a catch, which, not being straightforward, is a possibility. If we explicitly separate the robot system and the environment, which we didn't do yet, we can say that there's the robot system controller, I should say, because part of the robot system can be part of the environment. We can have the state of the system conditioning our reliability of the task. So it's reliability given that I am in state, say, x1. So this would result of the reliabilities, conditional reliabilities of f1 given x1, f1 given n minus 1 given fn and x2, and so on and so forth, until f1 given f2, fn, and xn. That is the state where I was when I had applied all the functionalities before. Now, here I can assume with some more certainty that these are state conditional independent functionalities. Of course, I have to compute them for different states. But it's like if I know the state at which I arrive at the handle, I can compute the reliability without changes of my picking object functionality. And in this case, they would all be independent, and I could just do the product of all of them, which is much nicer. So I can do the reliability of the task given the state as the product of the reliabilities of all the involved algorithms at the states when they were applied. By the way, for the cost, this is supposed to be simple. If the functionalities are concurrently executed in parallel, I only have to compute the maximum of all the costs of them. If they are sequentially executed, then I can add up the costs. But I just divide them by the number of things that I have added up, the ones that are sequentially executed, so that I keep the cost normalized between 0 and 1, so that it is balanced with reliability, which is always also 0 and 1. Remember, I made J as equal to C minus R. So let's go back to our example. Here, the cost would be the cost of F1 followed by the parallel execution of F2, F3, and F4, followed by F5, F6 in a sequence in parallel with F7, and after that F8. So I just use the formula. It's the cost of phi of F1 plus the maximum of this plus the maximum of the summation of these and F7 plus the cost of phi of F8. While the reliability would be the product. This is the shorthand. I should probably correct it to be more precise. This is, of course, the shorthand for the reliabilities given that I know the state. It's simply the product of them all. And then I could use the reliability of the task and the cost of the task, and I would be able to compute by propagating, that's the way I did it, the reliabilities and costs of the functionalities. I would determine the performance of the task. And as I said before, I then could even compare it with if I would just compute directly the reliability and the cost of the task without propagation and see if that makes sense. And more than that, I could do things like studying the robustness of my plan to changing a given functionality. Things that people usually discuss but never quantify is, okay, I'm having this robot in a factory moving around, picking objects and taking them elsewhere, picking in place. But the thing is how much the precision, the accuracy of my localization affects the performance of the whole system. Do I really need to consume a lot of CPU, which is a cost, to have sub-millimetric accuracy, or some kind of centimetric accuracy is enough? We should discuss these kind of things, and that's when we look at the system as a whole and can study the impact of these functionalities to design the system. So we can even do design by analysis if we succeed to do that. Design by construction, sorry, from specifications. Just a quick note to get back to the sequential decision making under uncertainty, because it's so well known, and explain why we could not use our methodology there, because it does the summation of the J's, and in fact it does not, we do not always do the summation of costs, and for sure we do not sum up reliabilities. In fact, we do their product eventually. However, if we use, instead of the reliabilities, the entropy version, the entropy is additive. So I'll say this without proof and very quickly, but entropy, which is, and I came back to this because George Saridis' or should I say, endeavor was to use entropy to quantify the performance of systems with a level of intelligence, not just restricted to lower levels of control. And in fact, using entropy in this case is additive, and that means we could use it for each of the functionalities and add them up to obtain the entropy of the full task using the sequential. We could use the cumulative discounted entropy and obtain the entropy of the full task as the performance, and then of course work out the costs in some other way. Just a quick note, this makes also sense because the unconditional entropy of a task that is h of ft only, not depending on the state, cannot be lower than the environment entropy. So what we can do is to minimize the entropy, but never below the level that the second law of thermodynamics forces us to. So, in conclusions, and I think I'm very fine with time, which makes me happy. I hope the organizers agree. Performance evaluation is something that people, so it's food for thought, should take in mind when assessing the quality of tasks and functionalities. People talk also about a lot about standardization. Of course, this could be a step in that direction, but it's more than that. It can be something that quantify different approaches in scientific methods to the solution of problems. If we do benchmarking, an interesting thing to do is to study the impact of functionalities performance on the task performance, given the definitions we use for functionalities and tasks. And we must be careful because functionalities are not in general independent of each other. And the big thing here was that I'm claiming that probability theory enables comparing different subsystems. That's the only way I can do the previous item. I cannot compare apples with oranges, but I can if I use probability theory and my definition of reliability and cost, which is consistent. And so I'm using a common a-dimensional language of uncertainty, which is uncertainty is common to all the subsystems in robotics. Well, the literature is basically the old paper, the old book by me and George, and then the recent paper in IROS, and papers that came out from the Rocking project with many authors from different partners, which explain something I did not go through here in much detail, but which is interesting, how to do benchmarking through competitions using the Rocking method of penalties, achievements, and definitions of task benchmarking and functionality benchmarking. So that's it. I think I have some time for questions. For now, I will